Welcome. Tonight this video explains what a Carrington-level solar superstorm is, how it forms and is detected, and how it would affect power grids, satellites, navigation, and the internet. Make yourself comfortable, like and save this video, and listen at a calm pace. Now, let us begin. Part 1. Basic elements of the Sun-Earth space weather system. Space weather is a group of physical processes that start at the Sun, travel through interplanetary space, and interact with Earth's magnetic field and upper atmosphere. The Sun emits a steady flow of charged particles called the solar wind. This flow carries a magnetic field outward and is shaped by the rotation of the Sun into a spiral pattern. Earth is inside this flow. Earth's own magnetic field creates a protective region called the magnetosphere. Disturbances occur when changes in the solar wind increase the transfer of energy into this region. The Sun is variable on human timescales. Dark sunspots mark areas with strong, twisted magnetic fields. Solar activity rises and falls in a cycle of about 11 years. During active periods, the Sun produces more eruptions. Two types matter here. A solar flare is a burst of electromagnetic radiation. A coronal mass ejection is a large cloud of magnetized plasma that leaves the Sun and moves through space. Only ejections that are directed toward Earth can cause strong geomagnetic storms. Travel time from the Sun to Earth ranges from about 15 to 20 hours for very fast events to several days for slow events. Near Earth, the solar wind brings the interplanetary magnetic field. Its strength is usually a few nanoteslas. When an ejection arrives, the local density, speed, and magnetic field can change quickly. A key parameter is the north-south magnetic component, often called the BZ component. When the BZ component turns strongly southward, coupling with Earth's field becomes efficient. Energy and particles then enter the magnetosphere and the ionosphere. Earth's magnetosphere is compressed on the day side and stretched into a long tail on the night side. A bow shock forms where the supersonic solar wind first meets the magnetosphere. During a storm, several current systems grow stronger. The ring current circles Earth. Field-aligned currents connect the magnetosphere and the ionosphere. Large horizontal currents flow at high latitudes in the ionosphere. Two simple indices help track the storm. The KP index ranges from 0 to 9 and reflects global disturbance levels. The DST index is given in nanoteslas and becomes more negative as the ring current strengthens. The ionosphere is a weakly ionized layer of the upper atmosphere. Its conductivity depends on sunlight, particle precipitation, and composition. During storms, the ionosphere becomes highly variable. Radio waves that reflect from it or pass through it can suffer loss, fading, and delay. These changes affect high-frequency radio links and introduce errors into satellite navigation and timing systems. Fast changes in the magnetic field at Earth's surface create electric fields in the ground. Long-grounded conductors pick up quasi-direct currents called geomagnetically induced currents. Power grid equipment is not designed for large direct currents. Even moderate levels can stress transformers and protection systems. Other long conductors, such as pipelines and some undersea cable power feed circuits, can also be affected. The impact depends on local geology, the length and direction of the conductors, and the rate of change of the magnetic field. Monitoring reduces risk. Ground magnetometers record magnetic variations in real time. Spacecraft watch the Sun and sample the solar wind near the L1 point, about 1.5 million kilometers upstream from Earth. These measurements provide short-notice warnings, often between 15 and 60 minutes before the strongest coupling. Longer-range prediction uses coronagraph images, extreme ultraviolet observations, and models that estimate the speed and direction of ejections. The exact magnetic orientation inside an approaching ejection remains uncertain until the structure is measured directly. Typical values set expectations. Average solar wind speed near Earth is about 300 to 500 kilometers per second. Fast streams reach 700 to 800 kilometers per second. Very fast ejections can exceed 1,000 kilometers per second. The dayside boundary of the magnetosphere is usually near 10 Earth radii from the center of the planet, but it moves inward during strong pressure pulses. Kp values of 7 to 9 indicate global storm levels. DST values below -100 nanoteslas mark strong storms. This part defines the chain from the sun to the ground. Eruptions change the solar wind. Efficient coupling transfers energy into the magnetosphere and ionosphere. Time-varying magnetic fields then generate currents in long conductors at the surface. Later parts use this base to map concrete effects on power systems, satellites, aviation, communication networks, and recovery procedures. Part 2. Historical examples and the Carrington scale. The Carrington Event of 1859 is used as the reference point for extreme solar storms. Contemporary records describe a very bright white light solar flare, followed by rapid magnetic disturbances at the surface of Earth. Telegraph operators across multiple countries reported uncontrolled currents on lines and in instruments. Some systems continued to operate after power supplies were disconnected, driven by induced currents alone. Reports of auroras came from unusually low latitudes. These observations show that strong coupling between the interplanetary magnetic field and Earth's field can occur and can drive large currents in long conductors. 19th century telegraph networks were long, grounded, and weakly protected. Their conductors formed efficient paths for geomagnetically induced currents. Operators noted shocks, overheating, paper ignition in recording devices, and erratic signaling. The technical architecture of those networks explains the impact: single-ended grounds, long spans, and minimal filtering. These conditions are not identical to present-day power and communication systems, but the physical driver was the same. Time-varying magnetic fields produced electric fields in the ground and in extended conductors. Another large storm occurred in 1921. Historical documents show widespread telegraph and telephone disturbances, railway signaling problems, and fires at equipment sites. The spatial extent of auroras again reached low latitudes. The 1921 case is valuable because infrastructure density was higher than in 1859, and records are more complete. It links extreme space weather conditions with early industrial-scale grids and communication lines and provides a midpoint between telegraph systems and modern networks. In March 1989, a severe storm produced large geomagnetically induced currents in parts of North America. The result included the collapse of a regional power grid after transformer saturation and protective trips. The event showed how reactive power demand can rise quickly when many large transformers enter a stressed state at the same time. Restoration took hours and required careful sequencing. This case connected space weather directly to modern power system operations, planning margins, and the need for procedures that match fast external disturbances. In late October and early November 2003, a sequence of strong storms affected satellites, radio systems, and navigation. Multiple spacecraft reported anomalies and safe mode entries. Low Earth orbit satellites experienced increased drag due to thermospheric expansion, which changed orbit predictions and raised collision avoidance workload. High-frequency radio experienced blackouts in some regions, and satellite navigation performance degraded due to ionospheric irregularities. The 2003 sequence provided a broad set of instrumented measurements for many subsystems at once and remains a standard training dataset. Fast transit from the Sun to Earth has been documented in several events. When coronal mass ejections are launched at very high speeds and maintain that speed, shock fronts can arrive in less than a day. Short travel time reduces the window for preparation on the ground and in orbit. It also increases the likelihood of abrupt pressure pulses that compress the magnetosphere and intensify the rate of change of the magnetic field at the surface. During extreme storms, auroras expand to much lower latitudes than usual. Historical notes, ship logs, and newspaper reports describe displays far from polar regions. This geographic spread is a practical proxy for the strength and reach of the ionospheric current systems. When auroras are seen at low latitudes, long conductors far from the poles may also be exposed to significant induced currents, even if the absolute magnetic perturbation is moderate. Comparative estimates of storm intensity rely on several indicators. For the 19th and early 20th centuries, direct magnetic recordings exist at some observatories but are sparse in space and time. Indices derived from those records can be reconstructed with uncertainty bands. For late 20th century events, indices such as KP and DIST are available continuously, and multi-point satellite measurements provide solar wind speed, density, and magnetic field. Witness reports of auroral extent and equipment failures complement the instrumented data and help constrain models of the historical events. Lessons for modern networks are consistent across cases. Long-grounded conductors are exposed to quasi-direct currents during rapid magnetic changes. Protection settings designed for internal faults can misoperate when presented with slow, DC-like bias. Large power transformers can overheat or lose voltage support when partially saturated. Satellite subsystems are vulnerable to surface charging, single event upsets, and increased atmospheric drag. Navigation and timing degrade when the ionosphere becomes irregular. Preparedness measures reduce exposure, improved situational awareness, operational playbooks, reserves of critical hardware, and training. Historical data have limitations that affect absolute comparisons. Instrument coverage was sparse in early periods, and calibration was not uniform. Many observations were qualitative. Reanalysis requires assumptions about local geology, conductor layouts, and network topology that no longer exist. As a result, numerical reconstructions of the 1859 storm vary. This does not change the main conclusion. Extreme coupling is possible, large-scale disturbances have occurred, and modern systems contain both new vulnerabilities and new tools for mitigation. Part 3. Physics of an extreme geomagnetic storm. An extreme storm begins when a fast coronal mass ejection, or CME, leaves the Sun and keeps a high speed through interplanetary space. The ejection drives a shock wave ahead of it. When this shock reaches near Earth space, the solar wind pressure rises quickly. The dayside boundary of Earth's magnetic shield, the magnetopause, is pushed inward. This compression is the first step. It raises currents on the boundary and primes the system for stronger coupling. A key factor is the magnetic field carried inside the ejection. The interplanetary
sedimentary magnetic field has a north-south component that forecasters call BZ. When BZ turns strongly southward and stays that way, magnetic reconnection on the day side becomes efficient. Reconnection is a process that joins lines of magnetic field from the solar wind to Earth's field.
It opens a path for energy and particles to enter the magnetosphere. A sustained southward BZ produces continuous input. Short, weak southward turns usually produce only modest effects. Once energy enters the magnetosphere, several current systems grow. The first is the ring current. It is a large loop of drifting charged particles that circles Earth near the magnetic equator. As the ring current intensifies, the ground magnetic field measured at low latitudes decreases. The DST index tracks this decrease in nanoteslas. A more negative DST means a stronger ring current and a deeper main phase of the storm. The ring current evolves on timescales of hours and then decays over many hours or days. At high latitudes, field-aligned currents connect the magnetosphere to the ionosphere. They close through wide horizontal currents in the ionosphere called electrojets. These ionospheric currents change the ground magnetic field rapidly. The KP index, which ranges from 0 to 9, increases as these disturbances spread in longitude and latitude. During extreme storms, electrojets move equatorward. Regions that normally do not experience strong ionospheric currents can be exposed to fast magnetic variations. The rate of change of the ground magnetic field is a primary driver for induced currents. Engineers refer to it as dB by dt. Large absolute field changes matter, but the fastest ramps are more important for geomagnetically induced currents in long conductors. When the field changes quickly, an electric field is produced in the ground. This electric field drives quasi-direct currents into grounded networks. The direction and strength vary by location and by the orientation of the conductors. Local geology sets how the induced electric field maps into actual currents. Rocks and soils differ in conductivity. Sedimentary basins and coastal regions with conductive seawater can support larger induced fields over wide areas. Shield rock with low conductivity can focus gradients along boundaries. The same external disturbance can therefore produce very different currents in two regions with different geology. Regional risk maps are built from conductivity models and past measurements. The length and path of conductors control exposure. Long, nearly straight lines collect more induced voltage end to end. Power grid transmission lines that span hundreds of kilometers are sensitive. Pipelines and railway signaling conductors also respond. Orientation matters. Lines aligned with the direction of the induced electric field see larger end-to-end voltages than lines at right angles to it. Network grounding practices and transformer connections further shape the current paths into substations. Power transformers are vulnerable because geomagnetically induced currents add a direct current bias to their windings. This bias can push the magnetic core towards saturation during parts of the AC cycle. Partial saturation increases reactive power demand, heats windings and structural parts, and distorts waveforms. Protection devices designed to trip for faults can misinterpret the distorted signals or operate with delay. If many transformers in a region enter stress states together, system-level voltage support can collapse and trigger widespread trips. Secondary effects follow from the primary saturation. Harmonics rise on the network. Relay measurements become less accurate. Capacitor banks and static VAR compensators see unusual loading. Operators must supply more reactive power to hold voltage. If
reserves are not ready, undervoltage can spread. In extreme cases, windings or leads can overheat, which risks permanent damage to the transformer. Replacement of large transformers takes time, so prevention and controlled operation are preferred over run to failure. Other long conductors experience different but related effects.
Pipelines can see changes in cathodic protection currents, which alters corrosion control and can trigger alarms. Undersea telecommunication cables carry data on fiber, which is immune to induction, but the repeaters along the cable need power from conductive pairs. Those power feeds can experience geomagnetically induced voltages and currents, especially in long spans at high latitudes or near continental shelves. The storm evolves through phases. The initial phase begins with the shock arrival and a sudden increase in ground magnetic field called the sudden commencement. The main phase follows when strong southward BZ sustains energy input. During the main phase, DST drops, KP rises, and ionospheric currents move equatorward. The recovery phase begins when the magnetic field turns northward or the solar wind pressure relaxes. The ring current then decays slowly and indices return toward quiet levels. Substorms, which are shorter high-latitude disturbances, can occur repeatedly during the main and recovery phases and add bursts of rapid change. Ionospheric conductivity changes over the course of a day and with particle precipitation. During local daytime, solar ultraviolet light increases conductivity. During storms, precipitation at high latitudes increases it further. Higher conductivity allows larger horizontal currents for the same electric field. This can intensify ground magnetic changes and the induced electric fields below. Nighttime conditions reduce conductivity, but rapid changes can still occur, especially during substorm onsets. Not all fast changes are global. Sharp spikes in the magnetic field can be local or regional. They are often linked to narrow current systems or boundaries that move quickly across the surface. From the perspective of a single substation, these spikes can be the most stressful moments, even when the overall storm is only moderate by global indices. Local monitoring at high sampling rates can detect them and support fast operational responses. Spacecraft near the L1 point provide the last upstream measurements. They record solar wind speed, density, and magnetic field. When they observe a southward turn of BZ and high dynamic pressure, operators can expect stronger coupling within tens of minutes. However, the exact internal structure of an approaching CME remains uncertain until it passes the spacecraft. This uncertainty is why forecasts provide ranges and scenarios instead of firm single values for peak impacts. In summary, an extreme storm is the result of efficient energy transfer from a fast magnetized solar ejection into Earth's magnetosphere and ionosphere. The most important physical ingredients are sustained southward BZ, high solar wind pressure, and long durations. Ground impacts scale with the rate of change of the magnetic field, local conductivity, and the geometry of conductors. Power transformers are stressed by direct current bias and partial saturation. Secondary effects include harmonics, reactive power swings, and relay misoperations. Pipelines and undersea cable power feeds also see induced effects. The storm unfolds in well-defined phases, and local spikes can matter as much as global indices for practical risk. Part 4. Monitoring and forecasting. This part explains how the space weather chain is observed and how alerts are produced in time for action. The goal is simple: detect an eruption at the sun, track its travel, measure the solar wind just before it reaches Earth, and translate those measurements into clear operational guidance. ground instruments provide the first layer. Magnetometers record changes of the magnetic field at the surface. 1-minute streams show the general trend. Higher rate streams capture fast spikes that drive induced currents. From many stations together, global indices such as KP and DST are computed. Other ground sensors add context. Ionosondes probe the ionosphere to derive electron density profiles. Networks of navigation receivers estimate total electron content along satellite paths. High-frequency radars map ionospheric flows at high latitudes. Rheometers watch cosmic noise absorption to track particle precipitation. Together, these data show how the upper atmosphere responds in real time. Space instruments provide the second layer. Solar telescopes in extreme ultraviolet show active regions, coronal holes, and flare locations. Coronagraphs observe the corona and reveal coronal mass ejections as they leave the sun. Heliospheric images track ejections farther from the sun and estimate their direction and angular width. Spacecraft near the L1 point sample the solar wind directly. They measure speed, density, temperature, and the magnetic field vector. These in-situ data are the last upstream checkpoint before the solar wind reaches Earth. Nowcasting uses the L1 measurements to give short-notice warnings. Typical lead time ranges from about 15 to 60 minutes, depending on solar wind speed and data latency. When the dynamic pressure rises, operators expect compression of the magnetosphere. When the magnetic field turns strongly southward in the BZ component, operators expect efficient coupling. The exact magnitude and duration are still uncertain, but the sign and trend guide the first set of actions on the ground and in orbit. Short-term forecasting before arrival uses remote sensing and models. Coronagraph images provide an apparent speed close to the sun. The estimated speed is corrected for projection and used as the initial condition. Drag-based models then predict travel time by assuming that fast ejections slow down toward the ambient solar wind speed. Magnetohydrodynamic models simulate the solar wind more fully and include stream interactions. Ensembles run many realizations with slightly different inputs to produce a range of arrival times. These methods give a window for preparation hours to days in advance. A fundamental uncertainty remains. The internal magnetic orientation of an approaching ejection is not known from images alone. The BZ component, which controls dayside reconnection, can be measured only when the structure reaches the upstream probe or Earth. For that reason, forecasts issued before L1 sampling use scenarios. They describe outcomes for sustained southward, variable, or northward BZ. Operators plan actions in tiers that match these scenarios and update them when in-situ data arrive. Translation from measurements to impact uses regional models. The rate of change of the ground magnetic field, called dB by dt, is estimated from magnetometer networks. Conductivity maps derived from geology convert magnetic change into electric fields in the ground. These fields are then projected onto long conductors, such as transmission lines, to estimate geomagnetically induced currents. Where available, direct sensors on transformer neutrals and pipeline potentials validate and refine the estimates in real time. Operational products are delivered in several forms. Text bulletins summarize current conditions and expected levels for the next intervals. Numeric indices give standardized thresholds for storm levels. Maps display regions of higher dB by dt and estimated ground electric fields. Machine-readable streams carry the raw and processed values for automated tools. Timestamps are in UTC. Update cadences are consistent and documented so that automated ingest can run without manual steps. Quality control and verification keep the system reliable. Incoming data are checked for timing errors, spikes, and dropouts. Models are tuned using past storms and quiet days. Forecast skill is measured with standard metrics such as arrival time error, false alarm rate, and missed event rate. When new sensors are added, the system is recalibrated. Operators are trained with historical replays so that displays and procedures are familiar before a real event. There are known limits. Some ejections are faint or directed in ways that make their speed hard to measure. So-called stealth ejections leave weak signatures near the sun. Data gaps can occur in ground networks or spacecraft streams. Single-point sampling at L1 does not describe spatial structure across the front. Multi-point observations reduce these limits, for example by placing additional monitors off the Sun-Earth line, but coverage is still incomplete. Forecasts therefore keep uncertainty bands and avoid single-value promises. Integration with operations follows a simple rule. Alerts are tied to clear actions. For power grids, thresholds trigger reviews of loading, reserves of reactive power, and staffing. For satellites, thresholds guide safe mode entry, attitude control margins, and scheduling of burns. For aviation, thresholds control polar route planning and radio backups. Communication paths for alerts are redundant and include dashboards, email, and machine interfaces. Drills rehearse the sequence so that updates from L1 can be applied within minutes. In practice, monitoring and forecasting work as a layered filter. Days ahead, images of the corona and heliosphere frame the risk. Hours ahead, propagation models provide an arrival window. Tens of minutes ahead, L1 measurements confirm pressure and magnetic orientation and set the final expectation. On the ground, regional models turn dB by dt into electric field estimates and into actionable numbers for specific assets. This chain does not remove the hazard, but it narrows uncertainty and supports timely, proportionate responses. Part 5. Power systems, vulnerabilities and protective measures. Electric power networks are exposed because they use long grounded conductors and large transformers. Rapid changes of the geomagnetic field create electric fields in the ground. These fields drive quasi-direct currents into transmission networks. The currents are called geomagnetically induced currents. They flow mainly through transformer neutrals and station grounds. Even moderate levels can push equipment into stress states if they act over large areas at the same time. Transmission lines collect induced voltage in proportion to length and orientation. Very long corridors accumulate higher end-to-end voltages. Lines aligned with the regional electric field see stronger effects than perpendicular lines. Grounding practices at substations set the return paths. Series capacitors change the effective impedance at low frequencies and can limit some direct components, but they also require controlled bypassing to avoid overvoltage or resonance during switching and faults. These details are handled by procedures before and during storms. Large power transformers are the main bottleneck. Geomagnetically induced currents add a direct current bias to the windings. The bias drives the magnetic core toward half-cycle saturation. When saturation begins, magnetizing current rises, waveforms distort, and additional heating appears in structural parts and windings. The effect is not a conventional short circuit. It is a bias that makes normal operation inefficient and hot. If many large units enter partial saturation at once, the system needs much more reactive power to hold voltage. Without reserves, voltage sags and protection trips can spread. Transformer design influences sensitivity. Three-phase core form units, shell form units, and banks of single-phase units behave differently. Autotransformers have direct electrical links between high and low voltage windings, which can pass more bias. Y-grounded connections provide a path for neutral current. Delta connections can block some harmonic components but do not remove the bias effect in the core. Thermal time constants are long. A unit can tolerate short periods of stress, but may overheat if bias and loading persist. Dissolved gas analysis and temperature trends after a storm help detect damage that is not visible immediately. Protection and controls must be considered. Differential relays use harmonic restraint to avoid tripping on inrush. During geomagnetically induced current conditions, even harmonic content can rise and confuse settings. Overcurrent relays may see distorted waveforms and respond slower or faster than expected. Tap changer controls can hunt when voltage sags slowly, which adds mechanical wear at a bad time. Static VAR compensators and STATCOM support voltage but can hit their limits or protective blocks. Capacitor banks may see high harmonic currents. Clear operating envelopes and preset limits reduce ambiguity when values move quickly. System-level effects appear as reactive power swings and loss of voltage support. Generators reach field current limits. Automatic voltage regulators work harder and may lower stability margins. If reactive reserves are not available, undervoltage spreads and forces load shedding or trips. HVDC converters are sensitive to waveform distortion and commutation failures. Fax devices and series compensation improve transfer capability in normal conditions, but must be coordinated under storm stress so that bypassing, blocking, and protection do not cascade. Monitoring turns a diffuse hazard into specific numbers. Transformer neutral current monitors measure geomagnetically induced current directly. Substation recorders track harmonics, voltage, and reactive power. Phaser measurement units add high-rate visibility of angles and frequency. System operators view regional dB/dt estimates from magnetometer networks and convert them into expected ground electric fields using geology maps. Where models exist, estimated electric fields are projected onto line routes to predict neutral currents at key substations. Alarms are tied to thresholds that map to actions in the operating guide. Pre-storm posture reduces exposure. Non-essential maintenance on critical corridors is deferred. Additional generators with strong excitation systems are started to raise reactive reserves. Synchronous condensers, SVCs, and STATCOMs are brought online. Voltage schedules are set at the upper end of normal. Long lines that run parallel to the expected electric field direction are reviewed. If alternatives exist, flows are rerouted to shorten effective exposure. Spare transformer cooling fans and pumps are tested. Staff levels are increased, and control rooms review the storm checklist. Actions during a storm are simple and repeatable. Hold voltage within the agreed band. Watch neutral currents, reactive margins, and harmonic alarms. Reduce loading on transformers that show high bias, current, or hotspot rise. Pause non-urgent switching to avoid unnecessary transients. Coordinate with neighboring operators for support and topology changes that lower exposure on long east-west or north-south paths, depending on the regional field direction. If undervoltage persists, apply predefined steps for controlled load reduction instead of waiting for automatic trips. Hardware options exist but must be planned early. Neutral blocking devices insert capacitors or specialized circuits in transformer neutrals to block direct current. They require bypass paths for faults and careful protection design. Neutral grounding reactors can limit neutral current but change fault behavior. Additional thermal margin in new transformer designs improves tolerance to short periods of bias. Temperature and gas sensors embedded at manufacture improve post-event assessment. For series compensated lines, fast and reliable bypass systems reduce the risk of unwanted resonance during stressed conditions. Spare part strategy is a major element. Large power transformers are custom units with long lead times. Logistics for transport and site preparation can take months. A regional or national stock of transportable spare units reduces downtime after damage. Standardized interfaces, spare bushings, and spare tap changer components shorten repairs. Contracts for mobile generation and mobile reactive devices add flexibility during restoration. Topology and grounding influence risk on a wide scale. Networks with many shorter lines have lower induced end-to-end voltages than networks built around a few very long backbones. Multiple ground points in parallel can dilute local current, but they also change fault paths and protection logic. Coastal regions and sedimentary basins tend to see larger induced electric fields than shield areas with low conductivity. Planning studies combine these maps with power flow models to identify substations where monitoring and mitigation bring the most benefit. Black start and restoration procedures assume that some areas may separate or de-energize. The sequence is well defined. Assess equipment condition. Build a cranking path from black start sources to target stations. Energize sections step by step while watching voltage and reactive power. Pick up essential loads in stages. Synchronize islands when frequency and voltage are stable. Throughout the process, keep transformer loading modest until neutral currents and harmonics return to normal. Document temperatures and alarms for later inspection and testing. Training and drills convert plans into action. Operators rehearse the data displays they will see, the thresholds they will use, and the calls they will make. Protection engineers test alternative settings in playback of past storms to confirm selectivity. Field crews practice safe switching under low voltage and high harmonic conditions. Communication with other sectors is maintained because telecom and fuel supply affect restoration speed. In summary, exposure in power systems comes from long conductors and large transformers. The main physical mechanism is direct current bias that causes partial saturation, extra heating, and heavy reactive demand. Monitoring of neutral currents and harmonics, clear operating guides, adequate reactive reserves, and pre-planned topology changes reduce the chance of widespread voltage collapse. Durable hardware choices and a credible spare part program shorten recovery if damage occurs. Part 6. Satellites, orbits, and navigation. Space weather disturbs satellites in three main ways. First, it changes the radiation environment and raises the rate of electronic upsets. Second, it increases the density of the upper atmosphere and adds drag to low Earth orbit. Third, it makes the ionosphere irregular and degrades radio propagation and navigation signals. Each effect has clear operational consequences for attitude control, power, communications, orbit prediction, collision avoidance, and user positioning and timing on the ground. Electronic upsets occur when energetic particles strike sensitive nodes in memory or logic. Single event upsets flip bits. Single event transients create false pulses. In severe cases, single event latch-up draws excess current and forces a power reset. Modern satellites use error detection and correction in memory, periodic memory scrubbing, watchdog timers, and redundant processors to contain these effects. Field programmable gate arrays are protected with configuration scrubbing. Software restarts keep services available but can reduce duty cycle during the storm. Charging is a second mechanism. In geosynchronous orbit and in high-altitude transfer orbits, hot plasma and energetic electrons can charge surfaces to different potentials. Differential charging leads to discharges across small gaps and damage to coatings or connectors. Internal or deep dielectric charging builds in insulating materials and can release later. Design measures reduce risk. Conductive outer layers, proper grounding and bonding, controlled surface resistivity, and minimized dielectric thickness help. Onboard sensors monitor environment and discharge events. Operations switch non-essential circuits off during the worst intervals. Power systems see two kinds of stress. Solar arrays degrade slowly with radiation dose and suffer temporary power loss during high flux events. Cover glass and cell layout set the tolerance. Power conditioning units see more noise when charging and discharges occur. Batteries must support longer safe mode periods if payloads are turned off and communication windows change. Thermal control faces additional load if attitude is altered to protect sensors or to reduce charging. Housekeeping margins are reviewed before storm seasons and adjusted during events. Attitude and orbit control are affected by both environment and operations. Star trackers can lose contrast due to increased background and particle hits. Guidance can fall back to coarse sensors. Reaction wheels and control moment gyros see more duty if drag torques increase at low altitudes. Thruster budgets must cover extra aerodynamic torque and more frequent orbit corrections. Safe mode attitudes often increase cross-section and drag. Teams plan safe mode orientations that balance power, thermal limits, communications, and drag exposure. Low Earth orbit is sensitive to thermospheric expansion. During strong storms, heating raises the density at typical satellite heights. Drag increases, orbits decay faster. Predicted positions diverge from catalog values sooner than usual. Conjunction assessment systems receive more alerts because uncertainties grow for many objects at once. Operators update drag coefficients, perform more frequent orbit determinations, and schedule small burns to hold altitude. Smaller satellites with high area-to-mass ratios are most affected and may re-enter if margin is low. Catalog maintenance becomes more difficult when drag rises. Radar and optical sensors must track more objects that are changing altitude and period quickly. Two-line elements lose accuracy faster. Screening volumes for close approaches become larger. False alerts increase. Coordination between operators, tracking networks, and traffic management services becomes critical. Short planning cycles replace weekly cycles. Maneuvers are timed to avoid peak uncertainty and to maintain safe separation from neighbors in the same shell. In medium Earth orbit and geosynchronous orbit, drag is not the main driver. There, the primary risks are charging, radiation upsets, and station-keeping errors from disturbed sensors or reduced ground contact. Satellites in geosynchronous orbit maintain longitude and inclination with regular burns. Disturbances in sun sensors or star trackers can delay burns or degrade pointing. Payloads with tight pointing budgets, such as high-throughput communication beams or optical instruments, may suspend service until stability returns. Operators increase link margins and switch to lower order modulation and coding during the storm. Communication links between satellites and the ground can degrade. At some frequencies, increased ionospheric variability changes phase and group delay. At higher frequencies, scintillation and rapid total electron content changes cause loss of lock and cycle slips in receivers. Uplink commands may require repeats. Downlink telemetry rates are reduced. Some operators switch to low-gain antennas, which are more tolerant of pointing error but reduce data rates. Schedules move non-critical high-rate dumps to quieter periods. Automated link adaptation is enabled where available. Global navigation satellite systems rely on stable satellite clocks, precise ephemerides, and predictable ionospheric delays. During storms, the ionosphere becomes patchy and turbulent. Receivers may lose lock on one or more signals. Code and carrier paths see fast delay changes. Differential networks that estimate corrections in real time are stressed when many stations experience rapid changes together. Single-frequency receivers that use simple ionospheric models show larger position errors. Dual-frequency receivers estimate and remove much of the delay, but residuals increase. Integrity monitors respond by raising protection levels or declaring reduced service. Timing receivers that depend on satellite signals for synchronization see increased jitter and more frequent holdover. Systems with good local oscillators ride through better. Mitigations exist for navigation users. Use dual or multi-frequency receivers when possible. Track multiple constellations to raise satellite count and geometry. Enable advanced integrity monitoring, such as receiver autonomous integrity monitoring or its augmented forms. Increase elevation masks to reduce low-angle paths that cross disturbed ionosphere at long slant ranges, accepting fewer satellites in view. For critical timing, combine satellite timing with local holdover oscillators and with terrestrial synchronization where available. Document performance targets for storm conditions so that automatic thresholds are known in advance. Operations planning reduces exposure for satellites. Before storm seasons, teams review environment thresholds for safe mode, payload shutdown, and high voltage bias reductions. They test memory scrubbing rates, reset paths, and configuration reloads. They verify star tracker settings for bright backgrounds and enable particle hit filtering. They pre-plan orbit determination with higher cadence and reserve fuel for altitude maintenance in low Earth orbit. They set communication schedules with more passes and flexible data rates. They confirm that ground stations have redundant paths and can switch modulation and coding quickly. During a storm, procedures are simple and conservative. Enter safe mode states on clear thresholds. Suspend high voltage operations on detectors that are sensitive to discharge. Reduce payload duty cycles to preserve power margin. Increase housekeeping telemetry cadence for temperatures, currents, and error counters. Raise the rate of orbit determination and prediction updates. Screen for conjunctions with tighter margins. Defer non-essential burns and deployments until conditions improve. Keep detailed logs of upsets, resets, link losses, and environment measurements for later analysis. After a storm, teams inspect for latent effects. They review error counts, reset events, and memory scrub statistics. They compare solar array power and battery performance to pre-event trends. They analyze orbit decay and fuel usage. They recalibrate drag coefficients and attitude control parameters. They restore payload high voltage levels in steps. They upload revised fault detection thresholds if performance changed. Lessons are integrated into the next operating guide and into design updates for future spacecraft. Ground infrastructure that supports satellites also adapts. Tracking networks adjust scheduling to increase pass counts. Data centers prioritize orbit products and conjunction alerts. Uplink stations validate time sources and switch to holdover if global navigation signals are degraded. Control rooms add staff and extend coverage. Interfaces with space traffic management and with power grid and telecom sectors are kept active because external outages can affect station availability and recovery. In summary, satellites and navigation systems experience higher rates of electronic upsets, increased drag at low altitudes, and degraded radio propagation during strong storms. Design features such as shielding, controlled surface materials, error-corrected memory, and robust power systems reduce sensitivity. Operational measures such as safe mode thresholds, flexible link settings, high cadence orbit determination, and conservative maneuver planning keep control through the disturbance. Users of navigation and timing improve performance by using multi-frequency, multi-constellation receivers, integrity monitoring, and local holdover. Part 7. Aviation, astronauts, and health. Space weather affects aviation through radiation dose, radio communication, and navigation. It affects astronauts through higher radiation exposure and operational limits on spacewalks. Procedures exist to manage these effects with route changes, alternative links, and shielding. This part describes the mechanisms and the standard responses. At flight altitudes, the main source of radiation is cosmic rays from outside the solar system. During strong solar events, large numbers of energetic protons add to the background for hours to days. Dose rate increases with altitude and with latitude. Polar routes see the highest values because Earth's magnetic shielding is weaker near the poles. Commercial aircraft structure provides some shielding, but it is limited. Airlines manage exposure by tracking accumulated dose for crew and by adjusting routes and altitudes during events. Dispatch and flight operations use alerts from space weather centers to plan polar traffic. When a strong event is in progress, dispatchers consider 3 options. The first is to reroute away from high latitudes. The second is to fly at lower altitudes than planned. The third is to delay departure. Each option has a fuel and time cost. The decision uses simple inputs: event level, expected duration along the route, and available diversion airports. Policies define threshold for action and for crew composition, including rules that apply to pregnant crew members. Radio communication on long polar legs often uses high-frequency bands that reflect from the ionosphere. During storms, increased ionization and particle precipitation cause absorption and blackout on some paths. Controllers and pilots switch to alternatives. Options include satellite voice and data, VHF relays when within range, and predefined reroutes that keep aircraft within line-of-sight coverage. Standard phraseology is used. Flight plans include contact procedures in case of loss of the primary link. Dispatch monitors link quality reports and can propose altitude or latitude changes to restore communication margins. Navigation performance can degrade when the ionosphere is disturbed. Satellite receivers may lose lock on one or more signals or show jumps in delay. Aircraft manage this by using multiple constellations, by relying on dual frequency receivers, and by falling back to inertial reference systems and radio navigation aids where they exist. Required navigation performance values and alert limits are enforced by onboard monitors. If integrity cannot be maintained, Procedures call for route segments with lower performance requirements or for altitude blocks with more separation. Aircraft avionics are built to tolerate single event effects, but not all upsets are filtered. Energetic particles can flip bits in memory or disturb sensitive analog circuits. Design uses error-correcting memory, redundant channels, and watchdog resets. In operation, an occasional transient fault is cleared by reset or channel transfer. Maintenance writes up events for trend analysis. Space weather alerts raise awareness, but the avionics response remains the same. Detect, isolate, recover, and continue with standard checklists. For astronauts in low Earth orbit, exposure comes from trapped particles in the radiation belts, from cosmic rays, and from solar energetic particles during events. The station structure and equipment provide non-uniform shielding. Crews carry passive and active dosimeters. During strong events, procedures call for sheltering in better shielded modules, limiting time near thin shield areas, and delaying extravehicular activity. Spacewalks are planned for quiet conditions. Real-time radiation monitors guide go or no-go decisions and allow early termination if levels rise. Spacesuits provide limited shielding. During a solar event, suit exposure can rise quickly because there is no additional mass between the astronaut and space. For this reason, extravehicular activity is not started when alerts indicate a high probability of strong particle flux. If an unexpected rise occurs, the instruction is to return to the airlock without delay. Post-event checks include dosimeter review and medical follow-up if thresholds are reached. Mission design includes radiation quiet zones and storm shelters. In low Earth orbit, water tanks, food stores, and equipment are used to add mass around a small area for temporary shelter. For beyond LEO missions, dedicated storm shelters with higher aerial density are planned. Vehicle timelines include safe mode attitudes that reduce exposure from trapped particles by minimizing time in the South Atlantic anomaly when possible. Health management follows established occupational frameworks. Aircrew dose is tracked as an occupational exposure with annual and career limits. Pregnant crew have stricter limits. For passengers, single flight doses remain well below regulatory concern, but airlines avoid unnecessary exposure by using the same route and altitude policies as for crew. Astronaut programs use pre-flight baselines, in-flight monitoring, and post-flight assessments to track both acute and cumulative dose. Medical teams maintain records and adjust assignments to stay within program limits. Operational coordination links aviation, space operations, and ground infrastructure. Space weather bulletins are translated into simple actions: reroute, reduce altitude, delay departure, shelter in place, delay spacewalk, and increase monitoring cadence. Communication lines between dispatch centers, air traffic control, satellite operators, and spaceflight control rooms are kept active through the event. After the storm, debriefs collect data on dose, link outages, navigation alerts, avionics resets, and crew workload. Lessons are applied to the next revision of the operating guides. In summary, aviation faces higher radiation levels on polar routes, periods of degraded high-frequency communication, and temporary navigation uncertainty. Standard mitigations are rerouting, altitude changes, and alternate links. Astronauts face higher radiation exposure and operate with shelter and activity limits during events. Dosimetry, conservative timelines, and clear go or no-go rules keep exposure within program limits. The combined effect of these measures is controlled risk and predictable performance during strong solar storms. Part 8. communications, internet, and terrestrial ICT networks. Space weather affects communication and data networks through two main paths. The first path is radio propagation in the ionosphere, which changes with geomagnetic activity. The second path is electrical stress on long-grounded conductors and timing dependencies in network equipment. These effects can disturb shortwave radio, reduce satellite link quality at some frequencies, increase timing errors in cellular networks, and create alarms in undersea cable power systems. Power grid disturbances add a third, indirect path by removing primary electricity and forcing networks onto backup power. High-frequency radio, also called shortwave, depends on reflection in the ionosphere. During strong storms, the D layer absorbs radio energy at high latitudes, and particle precipitation increases that absorption further. Blackouts on certain paths can last minutes to hours. Operators switch to alternative paths, use lower frequencies that penetrate less, or suspend use of affected circuits. Maritime, aviation, and remote stations that rely on high-frequency service follow predefined rerouting and fallback procedures. Very low-frequency and low-frequency systems, which include some time signals and submarine communication, also change with ionospheric conditions. Daytime and nighttime paths shift, and phase and amplitude can vary. Receivers that discipline clocks from these signals apply wider filtering and increase averaging time during storms. Where possible, users combine multiple sources so that loss of one path does not remove timing entirely. Satellite communication links at L-band and S-band can be degraded by ionospheric scintillation and rapid changes in total electron content. Receivers may lose lock or require repeats at the physical layer. At higher bands such as C, Q, and K, the ionosphere is less important, and weather on Earth, like rain, remains the main impairment. During storms, operators of L-band and S-band systems raise link margins, lower modulation order and coding rate, and increase interleaving. Ground stations schedule more frequent passes and allow extra time for command and telemetry. Undersea fiber cables carry data on glass and are immune to induction in the fiber itself. However, repeaters along the cable need direct current power delivered on metallic conductors. Geomagnetically induced voltages can appear on these long return paths and cause protective actions or alarms in the power feeding equipment. Cable operators monitor voltages and currents, adjust set points to remain within safe ranges, and coordinate with landing stations to maintain continuity. On land, long-buried telecom cables can see small induced currents in sheath bonds and grounds. Modern systems detect these as status changes rather than as payload errors. The Internet core depends on precise time for switching, transport, and cellular access networks. Many base stations and network elements use satellite navigation systems as their primary time source. During storms, ionospheric irregularities increase delay variation and loss of lock. Timing error grows. Time division duplex cellular systems require tight phase alignment between cells. To maintain service, operators use holdover oscillators in base stations, distribute time over fiber with packet timing protocols such as Precision Time Protocol, and use synchronous Ethernet where available. Grandmaster clocks with high stability reduce drift. Networks raise alarm thresholds during storms and track error budgets closely. Data centers prepare for two classes of problems. The first is loss of utility power due to grid disturbances. Uninterruptible power supplies bridge seconds to minutes, and generators supply longer runs. Fuel contracts and logistics plans are confirmed before storm seasons. The second class is timing and synchronization. Clusters that need precise time for logging, trading, or distributed databases verify multiple time sources. They combine satellite timing, terrestrial network timing, and local references. During a storm, they lengthen acceptance windows for timestamps and avoid non-essential maintenance that would remove redundancy. Backbone networks on land are robust to induction for the optical payload, but still use long-grounded conductors for power and protection. Station earthing and bonding must remain within specification. Surge protective devices and isolation transformers reduce the path for quasi-direct currents into sensitive electronics. During storms, network operators increase monitoring of station ground potential rise, rectifier loading, and alarm rates. They postpone planned work that would place sites on single feeds or disable redundancy. Broadcast and public safety networks follow simple rules. If high-frequency service degrades, they switch to satellite or terrestrial line-of-sight links. If satellite beams at L-band show high fade or loss of lock, they select lower data rates and more robust coding. They maintain local recording and store and forward capability so that brief link outages do not remove critical announcements. Control rooms keep voice fallbacks ready and verify that paging and alert systems do not depend on a single timing source. Enterprise networks and industrial control systems experience indirect effects. If global navigation signals degrade, plant clocks and logs drift unless there is a local reference. If utility power quality worsens, sensitive drives and controls see more trips. Facilities reduce exposure by isolating timing from the public internet, using local primary references, testing holdover, and checking that automatic failover works between time sources. They verify grounding, cable shields, and surge protection at cabinets that connect long field lines. Operational practice ties measurements to actions. When alerts indicate likely ionospheric absorption at high latitudes, network control centers preemptively reroute high-frequency circuits and advise users to prefer satellite or terrestrial links. When upstream monitors at the L1 point report a strong southward magnetic field and high dynamic pressure, centers raise watch levels for global navigation timing and prepare to switch base stations to holdover. If power grid operators announce risk of undervoltage or load shedding, telecom operators stage generators, raise fuel reserves, and confirm cooling margins at critical sites. During a storm, procedures remain conservative. Increase link margins on affected bands, use robust modulation and coding, slow non-essential data transfers. Raise the cadence of telemetry for link status, error counters, and time offset. Prefer fiber paths with stable terrestrial timing for backhaul. Limit changes in network topology to reduce the chance of configuration errors during a high alarm period. Record all adjustments with timestamps for later review. After a storm, operators review performance. They check error rates, lost lock events, time offset logs, and power alarms. They compare behavior to previous events. They reset thresholds to normal values, remove temporary routing changes, and restore planned maintenance windows. They analyze where holdover was sufficient and where it was not, and they adjust oscillator classes or distribution design for the next season. In summary, space weather can remove high-frequency paths, degrade L-band and S-band satellite links, raise timing errors in networks that depend on satellite navigation, and create alarms in long-powered cable systems. Direct payload errors in fiber are rare. The main practical defenses are redundancy in frequency bands and paths, robust timing architectures that include holdover and terrestrial distribution, disciplined grounding and protection at stations, and rehearsed operating guides. These measures keep communication and internet services available or degrade them in a controlled way during strong solar storms. Part 9. Risk Governance and Regulatory Framework. Risk governance aligns technical facts with clear roles, thresholds, and actions. The objective is to reduce uncertainty and to keep essential services within defined performance limits during strong solar storms. The framework covers monitoring, decision-making, communication, documentation, training, and investment. It defines how agencies, operators, and suppliers use common scales and common timelines. Authorities and operators use standardized alert levels mapped to actions that are simple and verifiable. A typical structure has a quiet state, a watch state, a warning state, and an alert state. The watch state is issued when an event at the sun is detected and models predict possible impact. The warning state is issued when upstream in situ measurements confirm speed, pressure, and a southward magnetic component. The alert state is issued when ground indices and regional models show high rates of change of the magnetic field. Each state has an associated checklist for power, satellite, aviation, and telecom sectors. The checklists contain time marks, thresholds, and responsible roles. A national or regional coordination cell links sectors during an event. The cell collects current measurements, model outputs, and operator status. It distributes short, consistent summaries at fixed intervals. It uses plain language, fixed units, and unambiguous timestamps. It records decisions and the data used to reach them. It provides a single point of contact for international exchanges. When necessary, it escalates to emergency management structures, but it keeps technical channels open for operator-to-operator coordination. Standards translate the hazard into engineering requirements. Grid codes define how transformers, protection systems, and reactive power resources must behave when quasi-direct currents and harmonics are present. Procedures specify which instruments are required at substations to measure neutral currents, voltage, and harmonics, and how data are archived. Telecom standards describe timing architectures that include holdover oscillators, terrestrial distribution, and satellite sources, and how equipment must report loss of lock and time error. Aviation guidance connects space weather bulletins to route changes, altitude limits, and communication fallbacks. Satellite operation standards describe safe mode criteria, memory scrubbing rates, discharge monitoring, and data retention during and after storms. Regulators ask operators to maintain risk registers. Each register lists assets that are sensitive to space weather, the impact of loss or degraded performance, the mitigation in place, and the residual risk. The register is reviewed at least once per year and after any major storm. Risk acceptance is explicit. Where residual risk is above policy limits, operators propose upgrades or operational changes with cost and schedule. The register links to business continuity plans so that technical impacts map to service impacts and to public communication. Audits and exercises verify readiness. Audits check that monitoring works, that thresholds are up to date, and that procedures are current and accessible. Exercises use historical or synthetic data to simulate the hours before and during a storm. Control rooms practice checklists. Decision logs are reviewed. Communication paths are tested, including machine interfaces for automated ingest of alerts and indices. Exercises also test the interaction between sectors, for example, how a power alert triggers telecom and data center actions, and how telecom status feeds back to power restoration. Data policy supports both operations and science. Real-time streams from ground magnetometers, ionospheric sensors, and upstream spacecraft are shared with clear latency targets and metadata. Operators provide anonymized status fields that indicate whether key thresholds are crossed without exposing sensitive layouts. After the event, higher resolution data are shared under agreed terms for validation and model improvement. Version control and timestamps are applied so that post-event analysis can reconstruct the exact view available at each decision point. Procurement rules incorporate space weather resilience. New transformers include thermal margin and monitoring for neutral current, winding temperature, and dissolved gas. New substations include neutral measurement, harmonic measurement, and communication to control centers. New telecom sites include dual timing sources, holdover oscillators of a defined class, and tested packet timing. New satellites include charging control, error-corrected memory, and sensors for environment and discharge detection. Requirements state test methods and pass criteria. Suppliers provide evidence of qualification and long-term parts availability. Spare parts and logistics policies reduce restoration time. Power networks maintain shared stocks of transportable transformers or critical components with plans for transport, site preparation, and commissioning. Telecom operators maintain spare rectifiers, timing units, and antennas. Data centers maintain spare timing references, power modules, and network equipment. Agreements define how stocks can be shared during regional events and how costs are allocated. Drills confirm that spare units can be moved and installed within the planned windows. Financial instruments support resilience. Insurance contracts and service-level agreements include clauses for space weather events. Force majeure definitions are clear. Operators quantify expected downtime under defined scenarios and align penalties and credits with realistic restoration paths. Incentives support investment in monitoring, reactive resources, storm shelters, and timing redundancy. Public funding can support shared infrastructure, such as ground sensor networks and upstream monitors, because benefits cross sector boundaries. Public communication policy reduces confusion. Messages avoid technical jargon and give direct guidance. What may happen, which services could slow or pause, and which actions the public should or should not take. Status pages and broadcast channels are ready before events. Messages are time-stamped and updated on a fixed cadence. After the event, a short report explains what happened and what changed in procedures or equipment as a result. Consistent, calm messages keep demand on emergency lines low and support orderly behavior. Research and observation investment is part of the framework. Multi-point monitoring upstream of Earth reduces uncertainty in arrival time and magnetic orientation. Ground networks with higher density and higher sampling rates improve regional estimates of the rate of change of the magnetic field. Ionospheric sensors and navigation receiver networks improve delay and scintillation models. Data assimilation and ensemble modeling improve forecasts and provide uncertainty bands that operators can use. Open interfaces allow models from different centers to be compared in real time. Cybersecurity and space weather are kept distinct in procedures and reports. Both can cause loss of service, but the indicators and responses differ. Logs and dashboards label space weather-related alarms with specific tags. This reduces false cyber escalations during storms and keeps security teams focused on genuine threats. Joint drills confirm that both flows can operate at the same time without confusion. Legal and reporting obligations are aligned with technical reality. Incident reporting thresholds allow for controlled degradation during declared storms without forcing unnecessary shutdowns. Mandatory reports include clear fields for space weather conditions so that statistics do not mix different causes. Confidentiality rules permit necessary technical data to be shared with trusted partners during an event, while protecting sensitive layouts and commercial information. Education and training keep the framework alive. New staff learn the basics of space weather, indices, and the meaning of alerts. They learn how their system responds and which actions they control. Refresher courses include updates from recent storms. Cross-sector seminars explain dependencies, such as how telecom timing supports power system protection and how power quality supports telecom cooling and base stations. Training materials are written in simple terms and kept short so that they can be used during shifts. Performance metrics track readiness. Typical metrics include the latency and uptime of sensor networks, the accuracy of arrival time forecasts, the false alarm and missed event rates, the time to issue sector-specific alerts after upstream changes, the time to execute operator checklists, the percentage of critical sites with dual timing and holdover, and the number of drills completed per year. Metrics appear on dashboards reviewed by technical leads and management. Trends trigger corrective actions. International cooperation reduces cost and improves coverage. Space weather does not respect borders, and sensor networks gain value with wider reach. Data exchange with standard formats avoids custom one-off links. Joint missions share upstream monitors and ground processing. Mutual aid agreements cover spare parts, mobile generators, and temporary communication links. Common terminology and aligned alert scales reduce confusion for airlines, ship operators, and satellite users that operate globally. In summary, risk governance turns space weather knowledge into predictable behavior. Standard alert levels link to fixed actions. Coordination cells keep information consistent. Standards set equipment and procedure requirements. Risk registers, audits, and exercises keep plans current. Data policies support both operations and improvement. Procurement and spares policies shorten restoration. Insurance and public communication align incentives and expectations. Research investment reduces forecast uncertainty. Clear separation from cybersecurity avoids mixed signals. Metrics and international cooperation keep the system transparent and efficient over time. Part 10. Impact Scenarios and Recovery. This part assembles realistic impact scenarios, the order of failures, and the steps for stabilization and restoration. It uses the same chain of cause and effect described earlier. Triggers are a fast coronal mass ejection, high solar wind pressure, and sustained southward BZ. Ground stress is set by the rate of change of the magnetic field, called dB by dt, regional conductivity, and conductor geometry. Baseline severe scenario. A fast shock arrives. A sudden commencement is recorded on ground magnetometers. Within tens of minutes, upstream measurements at the L1 point confirm strong southward BZ. Kp rises to 7 or 8, and DST drops below -100 nanoteslas. Power system operators enter storm posture. Neutral currents and harmonics increase but remain within operating guides. Voltage is held using reactive reserves. Some long east-west or north-south corridors show higher bias, depending on regional field direction. Satellite operators report elevated single-event upsets, occasional resets, and temporary safe modes. Low Earth orbit drag increases. Orbit predictions age faster. Conjunction screening volume grows. Aviation reroutes a subset of polar flights and lowers cruise altitudes on others. High-frequency radio at high latitudes experiences blackouts. Cellular networks keep timing within limits using holdover and terrestrial distribution. Undersea cable power feed equipment reports alarms but stays within limits. Restoration actions are minimal. Most services remain available with degraded margins for hours to a day. Reinforced scenario with localized equipment damage. Coupling remains strong for many hours. dB by dt peaks several times. In power systems, multiple large transformers enter partial saturation. Reactive demand rises and stays high. 1 or 2 units overheat and trip. Protection blocks or bypasses some series compensation. A regional island separates to protect stability. Load shedding is applied in blocks to hold voltage. Restoration requires several hours. In orbit, increased drag lowers altitudes of small satellites with low area-to-mass ratio margins. Catalog errors force temporary expansion of conjunction thresholds. Some operators perform unscheduled orbit determination and small burns. Navigation performance degrades at low latitudes during ionospheric irregularities. Timing networks switch more sites to holdover. Data centers avoid maintenance that would reduce redundancy. Aviation maintains reroutes for the event duration and uses satellite voice and data in place of affected high-frequency paths. Public communication notes limited slowdowns and regional outages. Recovery takes 1 to 3 days after the main phase ends. Extreme scenario with widespread outages and long recovery. A very fast ejection arrives in less than a day. Southward BZ is strong and sustained. dB by dt spikes occur over large regions with conductive ground. Multiple extra high voltage transformers saturate. 2 or more units suffer thermal damage. Reactive power shortfalls cause voltage collapse in several areas. Islands form and black out. Black start plans are activated. Telecommunications experience partial loss, where backup power or timing is not sufficient. Some undersea cable power feed systems reach protective thresholds and require controlled set point changes. In space, many LEO satellites lose altitude faster than expected. Operators perform unplanned burns to maintain shells. Catalog maintenance is difficult for several days. Navigation systems raise protection levels and announce degraded service. Aviation suspends most polar routes and delays a small fraction of flights until alternate paths are available. Data centers run on generators where utility power is out. Fuel logistics become critical. Restoration of bulk power takes days. Replacement or temporary bypass of damaged transformers can take weeks. Full normalization of catalogs and navigation performance may take several weeks after density and ionospheric conditions return to quiet levels. Geographic distribution of impacts. High latitude regions see the largest ionospheric currents. Mid-latitude regions with conductive sedimentary basins and long coastlines can experience large ground electric fields. East-west lines are stressed when the induced field is east-west. North-south lines are stressed when the induced field is north-south. Urban areas with many shorter lines can be less exposed than regions that depend on a few very long backbones. Coastal landing stations for undersea cables need close monitoring of power feed voltages and currents. Sequence of failures and controls. First, shock arrival compresses the magnetosphere and raises pressure. Second, sustained southward BZ drives dayside reconnection and injects energy. Third, ionospheric currents move equatorward and intensify. Ground dB by dt peaks. Induced electric fields rise. Long conductors see quasi-direct currents. Transformers enter partial saturation. Harmonics increase. Protective devices reach limits. If reactive reserves are low, voltage support is lost. In parallel, LEO drag rises and orbit predictions diverge. High-frequency radio fades. Navigation delay residuals grow. Controls at each step are predefined. Hold voltage, reduce loading on stressed transformers, start additional reactive resources, switch timing to holdover, lower modulation order on satellite links, increase orbit determination cadence, and route aviation away from polar sectors. Stabilization priorities. Maintain electrical frequency and voltage in energized areas. Protect large transformers from thermal damage. Keep at least one robust timing source per region. Preserve cooling and fuel supply for data centers and telecom hubs. Maintain two-way voice for emergency services. Keep ground links with satellites and update orbit products. Provide clear public status updates on a fixed cadence. Defer non-essential switching and maintenance. Black start and power restoration. Assess equipment condition using neutral current logs, temperatures, and dissolved gas where available. Build cranking paths from black start sources to target stations. Energize trunk lines and bring reactive resources online. Pick up essential loads in blocks. Synchronize islands when voltage, frequency, and angle are within limits. Keep transformer loading modest until neutral currents and harmonics fall. Replace or isolate damaged units. Document all alarms and temperatures for post-event inspection. Telecom and data restoration. Confirm site power. Start generators when needed and verify fuel. Switch base stations to stable timing sources. Revert temporary routing once backbone stability returns. Restore planned modulation and coding on satellite links. Clear store and forward queues. Verify paging, emergency alerts, and public status pages. Remove temporary alarm thresholds and return to normal cadence. Space segment and navigation recovery. Increase orbit determination until drag returns to pre-event levels. Update two-line elements or precise ephemerides with higher cadence. Perform maintenance burns to recircularize shells or maintain altitudes. Reacquire lost spacecraft and verify health. Restore payloads from safe mode in steps. For navigation, lower protection levels when ionospheric variability decreases. Review lost lock events and timing offsets at ground networks. Update integrity models as needed. Indicative timescales. Shock to first operational alerts. Minutes. Main phase stress on ground systems, hours to a day. Power restoration after regional trips without equipment damage, hours to 1 day. Replacement or bypass of damaged extra high voltage transformers, weeks. Catalog and conjunction assessment normalization after strong drag, several days to a few weeks. Navigation performance return to nominal, hours to days after ionospheric quieting. Full post-event inspection and report, weeks. Temporary workarounds, mobile generators and mobile reactive devices support substations and data centers. Portable high-stability clocks maintain local time where satellite timing is degraded. Terrestrial precision time protocols and synchronous Ethernet distribute time when satellite signals are unreliable. Satellite phones and line-of-sight radio provide voice fallback where high-frequency paths are blacked out. Store and forward and local caching reduce sensitivity to intermittent links. Public status pages and broadcast messages are mirrored across multiple platforms. Metrics for ending the event posture. Ground dB by dt below predefined regional thresholds. KP decreasing and below sector-specific levels. Neutral currents and harmonics at substations return to baseline. Navigation loss of lock rates and time offset errors fall within normal ranges. Orbit prediction residuals stabilize at pre-event values. Aviation returns to planned routes without special communication procedures. Control rooms close storm checklists and return staffing to normal levels. Post-event analysis collects synchronized logs from power, telecom, satellite, aviation, and navigation sectors. Reconstruct the timeline with UTC timestamps. Compare forecasts and alerts to measured values. Identify thresholds that were too high or too low. Update operating guides. Adjust hardware specifications where sensors or margins were insufficient. Add training points to exercises. Share anonymized data sets for model improvement. Long-term improvements. Increase upstream monitoring density to reduce uncertainty in arrival time and magnetic orientation. Add ground magnetometers with higher sampling rates in regions that show the largest induced fields. Improve conductivity maps used for electric field estimation. Upgrade transformer thermal margins and neutral monitoring in key substations. Expand timing architectures with dual sources and higher class holdover oscillators. Improve orbit determination pipelines for high drag periods. Maintain shared stocks of transportable spares and pre-approved logistics plans. Summary. Impact scales with coupling strength, rate of magnetic change, regional conductivity, and conductor geometry. 3 scenario tiers describe most outcomes: severe but manageable, reinforced with localized damage, and extreme with long restoration. Stabilization focuses on voltage, timing, communication, and controlled operation. Recovery follows fixed sequences for power, telecom, space, navigation, and aviation. Clear metrics end the event posture. Post-event analysis and targeted upgrades reduce exposure for the next cycle. Thank you for listening. This concludes the guide to Carrington-level solar superstorms. If it was useful, like and save this video for later. Stay prepared and have a calm evening.